Alright, and here's our last video of week 12, hopefully a little shorter, but this video is going to discuss what I call the closed region method, and the idea here is that I kind of cheated in the last video. Not really, but I kind of knew that we were going to find an absolute min-max, and you might have said, well, of course you were, Professor Bright, why else would we have done that example? And remember that we had this idea back in single variable calculus about having a continuous function on a closed domain attains its absolute min and max. Well, yes, that kind of works in multivariable calculus, but the fact that we're dealing with surfaces is a little different. What we're actually going to use instead of a closed set is the descriptor of compact. Okay, that does mean something very specific, and I'm going to tell you closed is a part of it, but we actually needed something a little bit more. Okay, and so in here, we're not going to discuss this formally until next semester, this language of compact. There is a theorem that we are going to kind of exploit right now, and it's a very famous theorem in analysis called the Hein-Borel theorem. And what that theorem says is that if a domain X is compact, that idea of compact is the same as if saying that that set is closed and bounded. Okay, so we're going to focus on these these ideas informally, and so next semester we'll talk about them more in depth. But the basic idea is that for right now, what I want you to do for closed is just to think of that the region includes its boundary. And for bounded, the idea is that, well, we're going to kind of define it in terms of antonyms. So if it's bounded, then it doesn't stretch to infinity. So it's kind of saying that, yeah, it's kind of saying it is not unbounded. Okay, but again, these ideas are kind of the foundations of what we talk about as topology, and so we'll talk about that more next semester at the very beginning of the semester. And then just to provide some quick examples here, I have a few different figures. I want you to pause the video and see if you can identify which of these are closed, bounded, not closed, not bounded. Okay, so the first one, it is meant to be the unit circle where you do not include the boundary. So the fact that it does not include the boundary, we would say it is not closed. And so that antonym, we say, well, if it's not closed, we're going to call it open. Okay, and this one, since it doesn't stretch to infinity, we would say that this is bounded, and my abbreviation for bounded is BDD. I don't want to write it out, so just my own shorthand. Okay, second one, you can actually see, well, okay, half of the boundary is included, but not all of it. We still have to, so we can't really say it's open or closed. We would say this is both open and closed, so it's kind of awkward. We don't really identify anything to this one, so we're going to say nothing in terms of open or closed. We would still say that this is bounded, though, okay, because it does not stretch off to infinity. Okay, so this next region, you can see that it does include its boundary. So we're going to say that this one is closed, and then it is bounded. So then this one, therefore, is compact. Yay, compact. Okay. Okay. Then in the lower left here, right, we have a region. Its boundary is this dark blue line, and since it is included, we would say that it is closed, which is kind of weird for us to say, even though it stretches off to the other side, but since it does stretch, we would say that it is unbounded. Okay. The next one, it does include its boundaries by the solid blue lines, and so therefore I would say that this one is closed. But then since it does stretch off to infinity in both directions vertically, I would say that this is unbounded. Okay, and then the last one should be closed and bounded, and then therefore it is compact. Yay, compact. Okay, then so that was just a brief summary of closed and bounded and all those ideas. And then just to talk about the compact region method, this is our three-dimension, or our 3 and higher dimension equivalent to the closed interval method, and that uses the idea of compactness. And so then if we're talking about a region or a function on a compact subset, okay, so we're restricting that somehow, what we want to do is optimize on the inside of the set. So that's the idea of find the gradient. Okay, so this is find the gradient, set it equal to 0, and then do the second derivative test. Okay, and then after this, so that would give us some idea about mins, maxes, saddle points, etc. Then after this, once we do that, then we need to optimize on the boundary. So then we want to parameterize first, and then once we parameterize, plug it in or sub into function. And then again, and then do number 1 all over again, okay, with that new thing. And then for 3, we would look at the function values. Okay, I want to emphasize that, not the x or y, but what we get for the function. And then we say that the largest is the max, absolute max, smallest is absolute min. Okay, then as a quick extension question, what if our region isn't one nice shape, right? In our example that we did, we were looking at the unit circle. We can parameterize that quite easily. What do you do in the case of something like this, where one side is maybe a parabola and then the other side is a line? What do you do? Answer: you have to repeat that second step, so optimize along the boundary for each piece of the boundary. Okay, so you need to break the boundary into pieces and work with each piece. Okay, so that's going to conclude the videos from this week. We will get some practice with that last concept in group work this week.